Yep, it's live now. Right, no, it's.
You're trying to avoid.
Yeah.
You think of the Oscars destroying your setup over? You think of the Oscars tearing apart your setup?
There's two on, actually. But I guess he forgot where S360 is.
Who's that?
You are, was all. Unless he's coming to Stanford, but not to the song.
Oh.
Almost. How's NOC going?
Oh, you're.
Good, a little tired, but.
Why?
I woke up really early.
There's no.
Yeah.
Yeah.
I don't understand why you come to life.
I did one was very, very, very close to the.
Yeah, actually, specifically, we want to check out one of the no, first time.
This is a very Cali like the 2 minutes beforehand.
Oh, yeah. Said that the faculty are gonna show up like 15 minutes later. Even though they changed the time on me last minute. Okay. There's apparently a little sheet in there that says pass or fail.
Yeah.
I hope he shoots pass.
Well, it depends on what you say.
So,
Yeah.
Yep. So, yeah, so, and then everybody leaves, and then,
And then we'll.
Yep.
That's why.
yes,
That's why I ask you. I will ask you to leave, and I will ask you back, right?
okay.
I hope Mark comes.
Yeah, really. The upper raise the possibility that he may not be coming. Changing the time on me.
I think he was in like a rush to get them like in the building. I think he was in a rush to get them in the building. And
I've never seen Tony.
I've never seen myself like this.
They're not all like meals.
Alright, just finished that 4-hour teleconference, scoring,
It's just, they do like breakfast English. It's good. It's just, they do a walker and then.
I took, I signed off for the last 2.
In order to get the rest of the one go. Yeah, and also they.
Is that right? It's pretty good. Now, which section? Please don't want to discuss them. What's discussing?
I have never, I was never on.
Thanks for coming.
Let's move back yesterday.
From Harvard.
Yeah, I didn't.
Now I find it actually, I want to take this trip to leave. No more than 3 nights.
Yeah.
Mike is right there.
You don't need.
Mike is over there.
So 3 nights actually, I come back very easy. And there, struggling to
It's been a while, so. Yeah, thanks for coming. I invited Lynn Lee as well, but I don't know if she's gonna make it.
It's crazy.
Huh?
The singer company is crazy.
Is that right? Marcus here.
right on time.
I'm ready to go.
Just the time of day.
I have a webcam here.
Yeah. So that's working.
Thanks for working.
All right, why don't we get started? Let's get started. So thanks to everyone who is here today, both those locally and those who come from afar and those who are even more distant. We appreciate your joining us today. It's a pleasure to introduce Tony Kim on the occasion of his oral defense. Tony has been a truly remarkable person to have in the lab, both from a scientific and engineering perspective, and also just as a wonderful contributor to the lab's intellectual environment. So Tony's going to be defending his dissertation today in electrical engineering, but I think what you'll see is that his work has been characterized by elements of many different scientific and engineering disciplines that would span aspects of mechanical engineering, computational engineering, micro-optics, and systems neuroscience. So this started a number of years ago. After a brief time in the lab, Tony approached me and said he needed, or he would request a certain number of months to go off to Mongolia, and hopefully I would keep a spot warm for him in the lab for his return, which I did, and it's been well worth it. This is a good time for him to be defending. Actually, one of his recent papers with Leach and Lowe's lab and Mark Wagner is just online at Cell. I think you're going to hear a little bit about that today. And so I think in the time that he's been here, I think you'll see that Tony has really mastered an incredible set of disciplines. And so with that, I'll turn it over to Tony.
Thank you, Mark, for the kind introduction. So my PhD work at Stanford has focused on advancing optical techniques for investigating the brain. As one can imagine, this is a very interdisciplinary goal, and over the years I had the opportunity to work with many biologists and engineers from Mark's lab and beyond. So today I'm particularly grateful for the opportunity to present our results to the wider Stanford community and to family and friends. The brain is clearly a very complex system, one that is truly multi-scale in a number of different dimensions. For example, the mouse brain contains 100 million neurons that are organized spatially at the macroscopic scale into large structures such as the cortex, the cerebellum, the brainstem, and so on. But at the same time, we can analyze the interaction of individual neurons in the local ensembles of hundreds to thousands of cells at specific parts of the brain, such as the layer 5 or premotor cortex, for example. Similarly, in the temporal domain, some processing of the brain take place at the millisecond timescale, for instance, the generation and propagation of action potentials. But on the other extreme, there are processes like learning that take place over much longer timescales as the brain adapts to new information over days and weeks and even possibly years. So given the immense complexity of the system, it makes sense that there are a variety of techniques that specialize in extracting information from the brain at different spatiotemporal scales. In this work, I'll be building on the technique of calcium imaging, which is particularly well poised to dissect brain networks at the cellular and subcellular level over an immense range of biologically relevant timescales. The basic premise of calcium imaging is to express a protein, for example, called GCAM, in neural tissue that reports the presence of calcium ions within cells by changing its brightness. In turn, the intracellular calcium concentration is a proxy for neural activity. It turns out that calcium is involved in the release of neurotransmitters at the ends of cells, for example, and hence calcium imaging allows us to read out the neural activity by taking movies of individual cells. This example video shows the correspondence between electrical activity and brightness. There is a wire attached to the cell that's going to read out the electrical activity as we take a simultaneous movie of the cell. The auditory beeps indicate the detection of individual active potentials. So as shown, the brightness of the cell increases during periods of higher electrical activity. By using standard microscopy techniques, we can then extend the field of view to cover local neural circuits containing hundreds of cells, not just one. So on the left, I show a diagram of a standard two-photon microscope that I built during my PhD. The diagram illustrates the standard architecture of a two-photon microscope, where the basic idea is to shoot an infrared excitation laser into the back aperture of a microscope objective. The objective, in turn, focuses this infrared beam into a single spot within the sample. The infrared spot excites the optical indicator of interest, for example, GCAM. We then collect the generated fluorescence through the microscope objective and deflect it using a dichroic mirror, which is a wavelength-sensitive mirror, into a highly sensitive photon detector, such as a photomultiplier tube. In two-photon microscopy, we then scan the point within the sample by tilting the beam at the back aperture of the objective, and by synchronizing the point scan and the signal from the light detector, we can reconstruct spatially coherent images of local tissue, as you see on the right. And so using two-photon with GCAM, we can collect movies such as these that show the activity of local neural circuits containing hundreds of cells. Once we've collected the calcium movies, the visual nature of the data set allows for tracking of single neurons over multiple sections. in the example up on top, the arrowheads point to track cells over the course of a week. And at this point in our field, we have a number of established computational algorithms for segmenting neurons from the calcium movies. The corresponding neural activity traces can then be examined at the single neuron or ensemble levels. So for example, in the bottom here, we have a very simple experiment where we image the visual cortex and computationally identify a number of cells. And we found that a large proportion of these neurons responded to visual stimuli indicated by the yellow triangle, as would be expected from this part of the brain. So due to its many advantages, calcium imaging has been exceptionally well suited to studies of local circuit dynamics. As shown previously, we have subcellular resolution readout of local circuits. We have sub-second temporal resolution so that we can correlate neural activity to various behavioral events. It is compatible with chronic studies over days and weeks and even longer. And without going into too much detail, calcium imaging is inherently compatible to a variety of different labeling strategies that can dissect neural tissue into various components by using genetic techniques and other biosensors like GCAM. So however, while this is all very great, I will argue that some key missing techniques have prevented the extension of calcium imaging to larger timescales. So by developing the requisite technologies, the aim of my PhD work is to extend the capability of calcium imaging to address distributed neural circuits located arbitrarily across the macroscopic brain. From a biological perspective, investigating distributed brain circuits is interesting because long-range interactions are ubiquitous within the brain. So a specific example of a distributed circuit discussed throughout this talk is the corticocerebellar pathway, which consists of cortex, pons, and cerebellum. On the right, I show a section of neural tissue where a viral payload has been delivered to the pons that highlights the regions that are involved in the corticocerebellar pathway. For example, the cortex to pons connection is shown in red, and the pons to cerebellum connection is shown faintly in green. So it may be a little bit easier to see the circuit in the cartoon representation on the top left, where the experimenters delivered retrograde pre-dependent TD tomato into an RBP4 mouse. So in this case, labels layer 5 cortical neurons that project to the pons. And local infection of GFP in the pons highlights the pons to cerebellar mossy fiber connection. So for members of the audience that are not used to looking at the mouse brain as much as some of us, these images are sagittal sections, sideways views of the brain. I've indicated the general shape and sort of the orientation of the mouse brain in relation to its head. So from the histological section, it is clear that the outputs of individual neurons, for example, from the premotor cortex, extend far throughout the brain's volume. Not only are distributed circuits present in the brain, they also form the basis of theoretical work that describe the possible interactions between brain regions and their potential computational function. Returning to our example, the corticocerebellar pathway, the pons to cerebellum connection has attracted extensive theoretical work owing to the unique synaptic connectivity within the circuit. In particular, the input layer of the cerebellum, the granule cell layer, have 4 fixed inputs. They are fixed for life, and they connect seemingly randomly to the mossy fiber inputs that emerge from the pons. The Mark-Albus theory abstracts these anatomical observations of the corticocerebellar pathway to build a mathematical neural circuit model. To summarize the model, the overall intuition of the theory is that for modestly high thresholds, multiple inputs of a granule cell need to be active in order for that granule cell to fire. In other words, a single granule cell is acting as a 4-way coincidence detector of 4 random conditions provided by its mossy fiber inputs. Ultimately, the function of the Mark-Albus circuit is then to project cortical activity into a very sparsely active, high-dimensional cerebellar space, which is believed to help signal classification by further downstream circuits. In addition to the corticocerebellar pathway, a variety of other biological functions are thought to be dependent on the interaction of regions throughout the brain. So for example, in action initiation and execution are thought to depend on the interaction of a variety of striatal nuclei, and the initial formation and long-term storage of memories are thought to depend on the interactions of the hippocampal system and various regions of cortex. Despite the scientific interest, we currently lack experimental tools for investigating network ideas with single-cell precision. Here, I'm going to show that calcium imaging can address this need by introducing novel engineering ideas that enable multi-axis imaging. And the techniques are going to be computer-aided surgical planning, application-specific micro-optic elements, and novel instrumentation based on robot design. So over the course of this talk, I'm going to describe 3 projects towards optical imaging of distributed circuits. So the first is the crystal skull. It's a surgical technique that grants us optical access to multiple cortical regions. Next, I'm going to be talking about the duopus, which is our name for a dual-axis 2-photon microscope that is based on relatively traditional optomechanical design. And in particular, I'm going to describe the first chronic studies of the corticocerebellar pathway with single-cell resolution that was just published yesterday. And finally, I'll be talking about the Octopus, which is a fully miniaturized, multi-axis robotic two-photon microscope for investigating 4 to 8 brain regions simultaneously. And as I describe these projects, I'm going to be highlighting the enabling technologies, namely, it's going to be CAD, micro-optics, and robots. So the crystal skull is our first large-scale CAD-informed surgery for accessing distributed circuits. At the onset of my work, around 2012, typical in vivo preparations only expose single brain regions with apertures only up to a few millimeters. So on the left, we have 2 examples of the cranial window technique where the idea is to drill out a small piece of bone to be replaced with optical glass. And on the right, we have an example of endoscopy, a technique pioneered by our lab that enabled deep region access by a miniature radiant index lens, or a grid lens. And as you can see, most of these examples involve optical apertures of a few millimeters. So then a natural question is, can mice even tolerate the extended surgical preparations that are going to be required for accessing distributed circuits? So with the crystal skull, our aim was to obtain single cell resolution optical access to multiple cortical regions by a massive window. However, as the effective diameter of the optical port increases, the 3-dimensional shape or the curvature of the brain becomes a practical issue. At the cortex-wide scale, a flat window simply can't close the gap at the edges, which comes from the fact that the brain and the skull is curved. And so an alternative approach might be to compress the brain, but again, at this scale, this will probably end up just killing the animal. So to accommodate the curvature of the skull, we established production methods for cutting and then curving glass, and then introduce a technique to the field. The cutting step more or less allows us to make arbitrary 2D shapes, and here we design one based on the outlines of the mouse skull. We then mold the flat glass against a cylindrical graphite mold to mimic the curvature of the skull. Working with Yanting Zhang in the lab, we developed surgical techniques for installing curved windows by sliding the implant under the bone to be replaced. The sliding technique minimizes expansion and compression of the brain during surgery, which we found to be quite important for resulting tissue health. We then confirmed the long-term health of neural tissue exposed by the crystal skull by in vivo measurements over weeks and with histological analysis. An important role that the Crystal Skull project played in my work is that it established for me a workflow of designing surgical preparations by CAD. The starting point of this approach was to segment a 3-dimensional model of mouse skull from volumetric CT MRI data that was publicly available. We then derived the shape and curvature of the crystal skull implant from CAD and validated against specimen measurements. Since then, I further developed the CAD approach by designing many other preps, not just the crystal skull, using computer modeling. And with many back and forths between design and implementation, we generally found that CAD models are not accurate to the level of anatomical targeting, sub-millimeter. Instead, at that level of precision, we need to close the loop with surgical and histological feedback. However, model predictions are accurate to about the millimeter scale, making CAD a very practical tool for surgical prep planning. So this video shows the extent of optical access we have through the crystal skull. The corresponding area of the mouse skull is indicated in the inset. This is clearly an enlargement over the few millimeter openings that were typically practiced during the earlier phase of my PhD. By overlaying a brain atlas, such as that from the Allen Brain Institute, we can see that the crystal skull provides an optical access to 20-something regions per hemisphere, including areas like visual cortex, auditory cortex, motor cortex, and so on. This is another video of the crystal skull at higher optical magnification and using a better camera. And this highlights the image processing techniques that can be used to enhance the appearance of single neuron activity in these type of data sets. So with the crystal skull, we have optical access to an estimated 1 million neurons from 30 to 40 brain regions, though not yet simultaneously. You can actually see at the edge of the video on the right, that edge of the field, the neurons become blurrier because the tissue at the edges rolls off the depth of focus for a single axis traditional instrument like this. Nevertheless, the crystal skull enables studies of cortical interactions, for instance, in multisensory paradigms and so forth. And for me, the crystal skull demonstrated the general usefulness of using CAD models for surgical planning and implant design, and also that large-scale surgeries required for distributed circuit access is going to be feasible in practice. In the next part of the talk, I would like to describe the Duopus, which is a dual-axis two-photon microscope. Dual-axis, as you see on the lower left, describes an imaging setup where we have 2 microscope objectives with independent mechanical degrees of freedom. This, in other words, there are 2 objectives about the mouse that can be positioned independently. And this contrasts an alternative optical scheme where multiple different subareas are addressed within one large imaging objective. Comparing the two strategies, the dual axis approach has a few unique capabilities. For instance, we have the ability to address arbitrarily widely separated areas. We are not limited by the typical size of a flat cranial window of up to 5 millimeters. And secondly, with the use of microendoscopes, we can address arbitrary combinations of deep and superficial brain regions. In fact, I would argue that the dual axis approach can actually take advantage of the complex geometry of the brain and is thus particularly synergistic with CAD-based surgical planning. So for example, earlier, I remarked that the curvature of the crystal skull resulted in significant defocus at the edges for a single axis top-down microscope. Here, with the dual axis microscope, we can actually use the curvature to further splay the objectives to better facilitate dual site imaging. Returning to our earlier example of a distributed circuit, this corticocerebellar pathway, working with Mark Wagner, a cerebellar physiologist from the Low Lab, we sought to experimentally characterize the corticocerebellar pathway in behaving animals with dual axis imaging and optogenic perturbation of the pons. So using CAD-based planning, we devised a surgical preparation that gave us access to simultaneous imaging access to the premotor cortex and the cerebellum, as well as bilateral optogenic manipulation of the pons. The additional details on the cerebellar implant, for instance, the polar and the azimuthal angle of approach, as well as all the details with regards to the premotor implant, generally indicate the level of detail that needs to be taken into account for implementing this type of multi-axis preparation. In addition to the implant placement, we used CAD models to confirm the viability of downstream imaging, namely that the microscope objectives would not collide at the prescribed orientations. Furthermore, we used the CAD models to squeeze out even an extra bit of space through which we could deliver optogenic light into the pons. We used a custom micro-optics for pons axis, which consisted of a miniature collimator lens and a 90-degree mirror to sneak in between the objectives for optogenic access to the pons during dual site imaging. With the dual axis approach, we image the output of the premotor cortex, layer 5 cells, simultaneously with the input layer of the cerebellum, namely the granule cells, namely the corticocerebellar pathway. And we did this for 2 weeks with single neuron tracking in both areas while mice learned and performed a 4-limb movement planning task, which involved pushing a joystick, as you see on the left, forward, and then turning the handle to the left or to the right for a delayed reward. So described earlier, classical theory more or less predicts that cortical activity should be transformed into sparse high-dimensional activity in the cerebellum. However, when we characterize the activity of single cortical and cerebellar cells during the task, we observe highly similar task tuning in both populations. So in the first column, we found that these cortical and cerebellar cells responded similarly to an upcoming left turn here. And in the next column, we found examples of cortical and cerebellar neurons that responded similarly to an upcoming right turn. And the proportion of total cells with this type of task-related activity was also similar in both populations. At the population level, the various different characterizations further highlighted the similarity between the two regions. So over the course of learning, the dimensionality of the ensemble activity actually fell at similar rates in cortex and cerebellum. And in fact, the dimensionality of the cerebellum was consistently lower than that of cortex, which already contradicts a little bit the Mar-Albus hypothesis. And as animals became more skilled at the task, the extent of behavioral encoding by neural ensembles covaried between the two regions as well. Furthermore, the strength of corticocerebellar coupling increased over learning and predicted behavior performance at the motor test, overall suggesting the emergence of a surprisingly shared dynamics across cortex and cerebellum that enhanced over learning, which was not predicted by theoretical models of the corticocerebellar pathway. An important caveat of all of this is that shared dynamics could be explained by a common input that goes into cortex and cerebellum rather than cortex to cerebellum transmission. To investigate whether the corticocerebellar pathway via the pons contributes to the shared dynamics, we performed optogenic inhibition of the pons during dual axis imaging of the cortex and cerebellum. As noted earlier, we used surgical planning and custom micro-optics to devise the means to provide optogenic light to the pons bilaterally, using the space between the two imaging objectives. So we performed optogenic inhibition of the pons in 20% of the behavior trials. On the subset of trials with pontine inhibition, we observed a loss of cerebellar task coding and reduced cortex-cerebellum correlations. Overall, these observations suggest that shared input into the two regions is insufficient to explain away the shared dynamics that we observed in the two regions. So to summarize our work on dual axis imaging of the corticocerebellar pathway, we use surgical planning, custom micro-optics, and dual axis instrumentation to achieve a 4-port optical preparation, 2 imaging, and 2 optogenetic in single subjects. With dual axis imaging, we experimentally observed shared corticocerebellar state that was not predicted by classical theory, and concurrent optogenic inhibition of the pons from dual axis imaging provided further evidence that pontine transmission contributes to the shared corticocerebellar dynamics. In the final part of my talk, I would like to describe the octopus microscope. So up to this point, we have now demonstrated the feasibility of addressing a few brain regions simultaneously using our engineering techniques. The next question is then, how do we extend our approach up to 4 to 8 regions to enable the next generation of neuroscience studies? I would argue that in terms of engineering, scaling to 4 to 8 regions requires 2 things. One, we need to have complete miniaturization of the imaging instrument. This is a very simple point, which is that if the instruments don't physically fit, then there's absolutely no chance of being able to image this many regions. And number 2, I would argue that enhanced instrument maneuverability is just as critical as miniaturization. Even if the instruments physically fit, we need an efficient way to be able to use them in practice to target multiple sites without being hampered by collisions that are bound to occur. To begin the discussion of miniaturization, here is a diagram of the standard 2-photon microscope that was introduced earlier in the talk. And as stated before, the basic architecture of a 2-photon microscope is that there is an excitation pathway that provides infrared light into the microscope objective, and that there is a collection pathway to collect the emissions from the sample back into a photodetector. So using micro-optic construction, namely grid lenses and microprisms and so forth, we reduce the physical size of a 2-photon microscope front end from 20 millimeters down to 2. The miniaturized front end also implements the standard 2-photon microscope architecture, again, where the excitation laser is brought in now from the side and couples into the micro-optic objective. And we also have a collection path for sensing emitted photons from the sample and to distribute it to a remotely located photomultiplier tube. As usual in the Schnitzer lab, we use optical simulation to achieve performance targets. Namely, we're aiming for a field of view of about 500 microns at most. We targeted an imaging depth of 100 to 300 microns in depth beyond the probe, and a numerical aperture of 0.5. We were able to achieve near diffraction limited excitation performance over the full field of view, at least in design. And we calibrated the light collection capability against the existing dual axis system. In addition to the initial design, I performed further rounds of optimization based on fabrication results. Namely, our production counterparts performed multiple runs of lenses 1, 2, and 3 that are involved in the excitation pathway. And we found an acceptable combination by selecting specific batches, even though the overall performance that you see on the right was degraded relative to the original design that you see on the left. The other approach here would have been to continue paying the company for further fabrication runs, which we could certainly have still do. And there are other opportunities for reclaiming the diffraction limited performance that we put aside for the time being. In addition to the grid segments, I designed and validated the performance of the 2 microprisms used in the system. And then we implemented a minimal 2-photon microscope to confirm the viability of the octopus front end for in vivo imaging. Using a reference target, such as the copper grid, we're readily able to confirm basic imaging performance in line with our expectations. We then applied the minimal microscope to in vivo targets and obtained live calcium imaging from the visual cortex and the prefrontal cortex as well. However, to properly deploy the octopus microscope in non-test configurations, we need to complete its mechanical packaging. We designed a 2-part housing to provide mechanical protection of the micro-optic front end with minimal excess bulk. The 2 parts clasp onto the micro-optic assembly, and we secure the optical elements internally by using a fiber-grade epoxy. Additionally, the housing provides additional mechanical interfaces, which are indicated in red for further assembly. And we're able to achieve all of this while adding very little excess bulk beyond the optical core. At the thinnest points of this housing material, the parts are less than 0.3 millimeters thick. We then use the metal 3D printing to accommodate unusual geometric requirements of the octopus front end. First of all, the 45-degree bend from at the input of the octopus front end is a tricky geometry to manufacture by conventional machining. Furthermore, we need to blend from the conventional circular shape of conventional optics into the rectangular profile of the octopus package, which is definitely tricky to machine conventionally as well. Finally, we implemented an attachment device for the collection fiber, And the final package octopus probe is shown on the right, which is now sufficiently secure in a mechanical sense to be deployed in true experimental environments. Having solved the miniaturization requirement, we now need to address instrument maneuverability. The basic requirement is that each microscope needs at least 5 mechanical degrees of freedom to access arbitrary targets in the brain. This is illustrated with the corticocerebellar preparation. For each objective, we basically need to be able to align the axis, which takes 2 rotational degrees of freedom, and then we need to be able to position the lens to its target in XYZ. Our prior implementation using serial kinematics for the arms couples the translational and rotational degrees of freedom, which is extremely unfavorable in terms of maneuverability. For example, consider the rotational axis indicated by the red arrow. As we actuate this rotational degree of freedom, there is gross displacement of the objective during angular adjustment. This, in turn, requires large compensatory translational movements to reposition the objective. And not only that, the microscope bulk will sweep through space during rotation with high chance for collisions. Practically, to address 4 to 8 brain areas simultaneously, it must be possible to align each imaging axis with minimal excess movement. The octopus microscope completely decouples the translational and rotational degrees of freedom by employing mechanical principles from the field of surgical robotics that face similar constraints. Namely, in minimally invasive surgery, there is a need to minimize the amount of translation at the incision point during tool actuation. So the octopus microscope is based on a remote center of motion kinematics originating from the field of surgical robotics. The idea of remote center of motion is to constrain the movements of a robot such that at a particular point, the remote center remains stationary during rotational motion. In the octopus microscope, I place that remote center at the tip of the microscope front end. Excitation light is then delivered free space through the robot, and optical alignment is maintained during rotational actuation. In fact, the full microscope, including the rotational degrees of freedom, was simulated in one ZMAX model. Here's an example video illustrating the pitch degrees of freedom of the octopus microscope implemented remote center of motion. Next, I show the performance of the remote center of motion kinematics in more detail. Here is the pitch degree of freedom. As well as the other axis, the roll degree of freedom. So combining miniaturization and maneuverability, the octopus concept is as follows. With its miniature imaging optics, we can pack multiple octopus front ends above a single behaving animal. And because the rotational and translational degrees of freedom are decoupled, we have the possibility of aligning each imaging axis to its target while minimizing the chance for collisions. Finally, I would like to demonstrate some in vivo imaging results using the octopus microscope. Here we use the robot microscope to image the dorsal CA1 through an implanted 1 millimeter diameter grid lens. We were able to see the calcium activity of about 100 neurons within the field of view. Next, we use the microscope to perform 2-color imaging in this striatum. For striatal imaging, these photos emphasize that the implant and the microscope are severely tilted, unlike conventional approaches. From this angle, it's also clear to see that we have miles of space above the brain for introducing additional octopus arms or other types of instruments. So to summarize our octopus results so far, we used an array of micro-optic components to miniaturize a 2-photon microscope down to the millimeter scale. We used remote center motion kinematics to decouple the rotational and translational degree of freedom that enhances instrument maneuverability. And we demonstrated in vivo calcium imaging with single-cell resolution in the prefrontal cortex, the visual cortex, the hippocampus, as well as dual-color imaging within the striatum. Looking ahead, we are currently applying the octopus approach to the study of 4 interacting brain regions. But from an engineering perspective, I believe that there are major opportunities in terms of techniques as well. So for example, The optical design of the optical's front end is naturally compatible with optogenetics to allow for read-write access to multiple nodes in the brain. I think that there are tantalizing possibilities for advanced micro-optical design involving additional complexities such as diffractive elements or nanofabricated elements. And finally, I think that there is a greatly expanded design space for surgical geometries taking advantage of enhanced instrument maneuverability. So overall, in my PhD work, by combining key engineering techniques, CAD, micro-optics, and robots, we have expanded single-cell resolution optical physiology to distributed brain circuits. Specifically, showed that large-scale surgical preparations to gain multi-region optical access is feasible in practice. We use multi-site imaging and optogenic perturbation to discover insights about how distributed brain circuits operate. And we established engineering foundations for the next generation studies of 4 to 8 brain regions. And so with that, I'd like to thank you for your attention.
Well, Tony makes it sound easy, but that's a lot of custom engineering. We have time for questions.
So I'm wondering how you, it was a great talk. I think you're extending this to flexible environments, so imagining imaging in the spinal cord or imaging in the hard to reach places, say in the midbrain. Do you think having these either micro-optic designs or using the CAD modeling will allow you to kind of extend it to neural spaces where it's hard to would actually get results with calcium imaging?
I think in terms of accessing regions like the spinal cord, I mean, in terms of space, there's miles of space away from the central nervous system, so I think that will be relatively straightforward. I think the techniques can definitely be extended, so I only showed the CAD models of the mouse skull, for example, but the other types of structures that we segmented involve entire bodies of mouse and so forth.
So how do you control for the depth of the imaging layers you're looking at? Because the brain has a depth structure on it, and if you're only looking from the peripheral area, how deep it can go?
That's a good question. So it turns out imaging through biological tissue is a major limitation of optical physiology. With two-photon microscopy, we can typically access the first 500 microns of tissue. If you wanted to reach, in principle, any deeper than that, there are a number of different techniques. So one, you can just remove the material up on top and to give yourself a little hole so you can dig in a little deeper. Another type of technique is endoscopy, which, as I mentioned, which came from our lab, where we can actually design additional optical elements that can be surgically placed within the brain to allow for very, very deep access. But of course, this involves some damage. But we control that not necessarily at the instrument, but by doing the surgical implantation of the device itself.
That's cool. All right, let's make Tony again. Okay, so we'll take a little break and then have the private session here in this room. And then on the presumption that all goes well, there will be a little celebration out on the balcony at approximately 2:45.
That went really fast.
Well, you know,
But I had to drop one. Yeah. Wow, that went really good.
because of the hell so it sounds pretty.
Yeah.
5 minutes for each report.
Oh, yeah.
Yeah. I'll see you after.
So, Tony, I'm just going to end the...
Oh, thanks. Really? So basically, I was so tired.
Tony, I'm just going to end the stream.
Yeah, sounds good. Bye. I don't know.